Hello, Dr. Chitlin and our TAs. My name is Nicholas Lee, and my colleagues and I go by the Linear Thinkers. Boom. During this presentation, we're going to go through a real-world problem in which we used graphical version of linear algebra to solve. So to start, we had to come up with an idea, and we decided to go with minimizing production costs. Now, I have over 7 years of experience working at a company that does manufacturing of cartridge valves, and I know firsthand that the bottom line is everything. There are two main ways to make money, right? There's either reducing the amount of production costs or increasing how much you sell. And one of them is more controllable than the other. So in the next coming slides, our team will discuss how we use linear algebra to show what amount of each product was used to create the lowest production cost total. Now, the numbers you're going to see are taken from a company called Sri Lakshmi Craft and deal with their two products, mono cartons and master cartons. And the quantities you're going to see are in units of 1,000. So every number just multiplied by 1,000. Now, I'll let Liam take it from here to start our process.
Thank you, Nick. My name is Lian, and I'm going to go over the problem formulation, which is the first step of the problem. The first thing that we got to do is identify what the problem is. Like we mentioned before, it's just minimizing the cost of production. And in this specific case, we're going to look at two products, and we're going to try to minimize the combined cost of this product. Now, of course, there's a lot that goes into minimizing cost. You got to look at labor costs. You got to look at the product type and the precursors. Some of these factors we're going to omit for the sake of time and simplicity, and we're going to focus on what we can control. So for example, in this case, the approach is to optimally balance the production number of these two products according to their price. So let's say product one and product two are X and Y respectively. The per unit cost of product one or X is going to be $8 and change, and the per unit cost of product Y is going to be about $50. Z is going to be the function of the production cost of each of these products multiplied by the quantity we're going to manufacture, and that's what we want to find out. So it would be 8.667x plus 50y. And if we can minimize this Z function, we have optimized the production cost of the factory. Now for the next section of constraints, I pass it over to my teammate.
Hello, Professor. My name is Jab, and I will go into the constraint of this problem. So we start by stating what are the possible constraints. For example, we can have material constraint, which is, of course, every product requires a certain amount of material, such as steel, plastic, or chemical, and if those are limited, they cap the total production. We then have the capacity constraint, which is some factories can only provide a certain amount of product every day due to energy or due to time working. We also have the on-demand constraint, which is to satisfy the contract or market need, you might need to produce a minimum number of each product. For example, on your column on the right, we must produce minimum of 300x and 60y. But one of the most important constraints is the priority constraint. So, in real life, some products can be in favor more than the other products. So we need to know the constraint, for example, by how many times a product X respectively should be produced more than product Y relating to favor or urgency. For example, we put down an example over here, X should be larger than or equal to 2Y, which is you must produce X at a rate twice as much as Y. Now, constraints are given by many detailed by manufacturing capacity, precursor cost, on demand, etc. And below are some functions that we point out for the constraint capacity. So for the next part, which is the value side, I will pass it down to my teammate, Paul, please.
And yeah, I'm from, so I will talk about the value side of constraint. So we have 4K constraint. So from the we have four corresponding line. For the first line is plus y equal to 65. The value side will be above the line. That means we have at least 265 units. For the second line, the value side will be below the line, meaning we have a a manufacturing capacity limit. And for the third of the four line, the valid side will be on the right of the vertical line and above the horizontal line. That means the minimum 300 unit of the product X and 60 unit of product Y. So from the constraint will create a special region on the graph. This region is called the feasible solution region. So I will hand over to Jem to talk about the feasible solution region.
Hi, I'm James, and I'm going to talk about the feasible solution region. So the feasible region is the area between all the different lines and their inequalities that satisfies all the constraints. And then the neat thing about the feasible region is that at each of the vertices, we can either find the maximum and the minimum of the constraint. So we use the previous constraints and we substitute to find where they intersect. And then when we substitute x as 300 into the 265 equation, and we get the 300 and negative 35. And then when we substitute y, we get 205 and 60. And then for the other equation, when we substitute, we get 300 and 15,900 and 1,620 and 60. And then for the final constraint, we get 360. And then at each of these vertices, we can plug it back into the z function. I'm going to pass it down to Mukunda.
Thank you, James. My name is Mukunda. I'll go into plotting the objective function. The objective function in linear programming is used to express the quantity that you either want to maximize or minimize. Our goal is to minimize total production costs, represented by the objective function z equals 8.667x plus 50y. The coefficients 8 and 50 are the costs per unit of products x and y, and z represents the total production costs that we're aiming to minimize. First, we have to plot the constraints that must be met for the production process. Then by plotting the function, we can identify the feasible region. The optimal solution occurs at one of the vertices of the feasible region where the objective function line just touches the feasible region. This graphical method demonstrates how production levels of two different products interact under given constraints. It simplifies the process of minimizing cost by converting complex algebra into a straightforward visual interpretation. I'll now pass it to Aiden to explain more about finding the optimum point.
Hi, my name is Aiden, and I'm going to talk about finding the optimal point. Finding the optimal point is the last step of this, where we find the amount of units to produce the least amount of cost within our feasible region. To do this, there are actually multiple methods. There's the main ones: ruler line method, vertex testing method, and graphical method. The ruler line involves plugging in different values for z, creating a line that goes across the graph, and just testing to see, finding the minimal point within the actual feasible area. This is useful and it's like very intuitive and visual way to do it. However, it is tedious and time consuming. There's also the vertex testing method, which involves looking at purely the vertexes of the optimal solution, or vertexes of the graph, and to the objective function and to outputting the values. However, for our case, we chose the graphical method, as it is just the best for our case, where we have two constraints, where we plug in the feasible region points, as was calculated earlier, into the objective function and finding the outputs. And to this, so now we find which has the lowest amount of output, which means it has the lowest amount of cost for that production, which we found to be 850. However, because the Y production was negative, which is impossible, we ignore that point and go to the next best, which is 5,600 with the units 300,000 for X and 60,000 for Y, with an actual production cost of 5,600. Now I'll hand it back over to Nick.
So throughout this whole process, we found multiple data points, which led us to the conclusion of 300,000 units of product 1 and 60,000 units of product 2. To do this, we formulated our problem use given constraints to find our feasible points, create a graph to show our feasibility region, and then calculate our lowest cost to produce the proper amount of each product. As we stated earlier, our world runs on money, whether it's a Fortune 500 company like Apple or a mom and pop shop like a sandwich shop down the street. But no matter how large or small it is, linear algebra can be used to solve problems to increase their bottom line so that they can make more money. Just a quick overview of our team responsibilities. We all decided to do research to help the process move forward. I created the presentation, Aiden did the project outline, Lian, James, and Jiap did the math of the real world problem, Fong found the constraints, and Mukunda graphed the real world example. Here is a list of all of our references used, and thanks for watching. We appreciate it.